This is the recording for the Unit 5 post lab. There are two different experiments here. One is stress and strain with the rubber band, and the other one is the hydrostatic pressure. So, of course, the first one here is, yes, you have attended the lab and have submitted things. This is the motivation for the stress and strain, and look at the lab manual, and the ones that I checked here, which I believe I checked them correctly, make sense when you look at it. This one here, this and the next one require you to use the Excel sheet that was supplied. You don't need your own data, but you would have to plug in these and these and then use the Excel sheet to compute all the rest. These might be given in my example. And then you just read off from the Excel sheet what the strain is. And it really doesn't matter if your lab partner happens to have the completed Excel sheet. You just put these data in here as example data, and it's a way to figure out that you understood what was going on with the Excel analysis. The next one is basically the same thing, different numbers here, and it's asking for stress. All right. Then this one here, kind of an analysis of what happened in the lab. So how should the Excel graph look like when you were done? If you have, especially if you have a lot of data, then it first gradually increased, and then it became quite steep in the shape of a hyperbola. The expansion of the rubber band follow Hooke's law? No, it doesn't. Hooke's law is, for example, for a spring or for a steel wire, where the more you put on, it proportionately increases in length. So it would be a straight line, and what you got there was definitely not a straight line. What happened to the expansion of the rubber band when a lot of weight was suspended from it? The rubber band barely expanded anymore. That's especially the case if you were able to put more and more weight on it, and then you came across this, wow, you were putting more weight on it, and it just doesn't expand anymore. And why doesn't it do it? And the explanation is over here. All right, the errors for the stress and strain, again, these make sense, the ones that I checked here. You may want to double check it though. So the not slipping, removing masses in between, measuring length, inconsistency in the rubber band, the masses used as loads. All right, the conclusion, I think there are only 3 parts for this one here. So this one here would be listing the results. Then this one here would be comparing the results. And then the last part right here then would be the error analysis. And this one is hydrostatic pressure. The motivation, again, when you look there, you will find these as the motivation. I think there are only 2. Then the concepts that you get for that lab. Why should the 2 speeds equal each other? And the explanation is when potential energy is transformed to kinetic energy and so on. That's why they should be the same. Why is the actual speed of efflux smaller than the speed of efflux due to the pressure after all? And you computed that and you came up with a fraction that was less than 1, so less than 100%. And here it is, the shape of the orifice affects the essential speed of efflux with which it exits. And then there's a little bit more here, surface tension, viscosity. You saw it spreading out, so there's viscosity there, there's air resistance there. So that all takes away kinetic energy, and hence the Vx is not the same as the Vp. What's the shape of the orifice? If you used a plastic bottle, then the hole was poked in by a thumbnail, and therefore it's sharp-edged and curling inside. If a tall tube was used instead, then the nozzle is pointed outward, where it allows for quite efficient flow. And let's see, that was the shape. What is the approximate expected orifice coefficient? So again, if it was a plastic bottle, it's probably around 0.60, and if it was the tall tube, then it's probably around 0.90. And there is some variation there. Okay, this one is that you understood the equations that were used. So this one is basically applies that the kinetic energy is the same as the potential energy, and so overall you basically just have to plug in the 982 times 17, then you multiply by 2. It's not this 2, it simply is a 2 that shows up because it used to be 1/2, and you divide by 1/2, which is times 2, and then you have to take the square root. So again, that equation is of course in the lab manual. This is the other equation that you will find. That's the one from the equations of kinematics. So you have to plug in these numbers here, the 86, the 982. I think, again, you have to divide by 1/2 or multiply by 1/2. Take the square root. And oh yeah, and then there's the distance, 66 centimeters in this case. And of course, you've got your own values. And then the errors that are associated with this lab, I believe there are 5 different errors. And again, they make sense when you look at them. And that was the recording for the Unit 5 post lab.